Okay. Tree-based methods. All right. So basically in this we've got decision trees, and then and extensions of decision trees is bagging and random forest and boosting. And random forest is very powerful, and we'll talk about that. But first, I guess we got to talk about decision trees. Okay. And so the idea of a decision tree is that you are going to split the data into smaller chunks. Okay. And it's kind of just like and you basically just group people into these different chunks, and you just treat everybody the same. Okay. And we do this a lot politically. I don't know, for demographics and stuff. And so you'll hear things like in the news, it will say like white voters voted this way and non-white voters voted this way. And they'll say things like female voters voted this way and male voters voted this way. And middle class voters voted this way and upper class voters did this way, or educated versus non-educated. And then they further do these things, and then they'll say like, okay, so and probably as I speak these things, I don't know how in tune you guys are with U.S. politics, but if you say like white, male, middle class, uneducated voter, and like uneducated meaning like that doesn't hold a college degree or something, then they'll say like these voters voted this way and stuff on this topic, and these are their opinions, and then you'll have something like female, non-white, educated, blah 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 voters often vote this way, and things like that, right? And this is basically the result of kind of decision tree kind of thinking, in that you just kind of partition the population into smaller groups, and then you just kind of treat everybody in that subsection the same way. Okay. And of course, it's not correct to say every single white, male, middle class, non-college degree educated voter thinks exactly the same way. But perhaps if you polled them and you said, would you vote yes or no on this proposition, you might get something like a 75-25 split. Okay. Whereas if you ask the general population as a whole, you might get something like a 52-48 split. Okay. And so the general population might be 52-48, which means basically it's fairly even. But then if you subdivide it into a certain group, you get something like a 75-25 split. And then that means you've basically reduced the amount of diversity of opinion there. Okay, you've kind of made the end result a little bit more. You might call it a purity index or something. Okay, things like and if you polled again, just kind of like the opposite group, female, non-white, and college educated voters, and you polled them on the issue, they might support it, 15% versus 85% or something like that. Okay, and again, having around 50-50 represents kind of maximum diversity, maximum like entropy or maximum mixing. And then basically when you get down to something like 80%, hold one opinion and 20% the opposite, then you're in kind of this minority split. And so decision trees are just kind of looking for where should we draw a line and split things so that the resulting groups are a little bit more homogeneous, meaning display less kind of mixing than the greater population as a whole. Yes?
So like in your example with voters,
yeah.
Like could you say that like race is an explanatory variable?
Yeah. So race is an explanatory variable.
So when it says it forms a binary split, does that mean there's only like, can you have multiple races or just two?
Yeah, so with the decision, the way we have decision trees, it can only be a binary split, okay? So it could be, you can do white versus non-white, black versus non-black, Latino versus non-Latino or something, but those each get their own splits, okay? So you can't do a split where white voters go in this one, black voters go in this one, Latino voters go in this one, and something like that. It has to be this versus not this.
But you can reach the same conclusions as you would if you had like all amounts at the same time.
Yeah. I mean, effectively, what we're talking about, you're talking about a split that goes like this, and here the split has to go like this. Okay. I guess like this, and so so instead of going A, B, C, D, it has to go like this. A versus not A, and then B versus not B, and then C versus not C, which has to be D or something like that. Okay, so you can achieve something similar, but all the splits have to be binary. Yeah. Okay. I mean, it doesn't. I mean, you could even do, depending on how it goes, you could go. Is it AB versus not AB, which in our case could be like C and D, right? And then you could split it this way. However it goes, the splits just have to be binary. That's how it goes. Okay, and and so for this voters example, that's a categorical response. Do you vote yes or no? But you can do numeric response, and these are called regression trees, and it's pretty much the same, except you just assign everybody the mean value for that thing. Okay, so this is kind of the idea. With linear regression, you are saying, when x changes, it's going to increase y by this much. With a decision tree, you just find a boundary. You say, we are going to draw a boundary at, some arbitrary number, and based on this number, we're going to treat the two segments differently. So for example, if you try to rent a car, okay, they will ask you, how old are you, right? And the rental car industry has arbitrarily decided, well, I don't know about arbitrarily, but has decided that 25 is the year that they will treat customers differently, okay? So if you're under 25, they charge you a higher rate because they say you are not as good of a driver or whatever, less responsible, whatever they say, right? They charge you a higher rate because you represent a greater risk to the rental car company. And if you're over 25, they charge you a lower rate, okay? And so, and this is basically a single decision tree based on age that says, on this numeric variable, if you're 25 and over, we will charge you this amount of money, and if you are under 25, we charge you this amount of money, okay? And that's kind of how it goes. So yes, question.
How is this different from the step function?
So yes, it's very similar, okay? It's very similar. It's just, so the result of a regression tree is, for a univariate variable is very much like a step function. It's Yeah, so well, you can have a bunch of cuts. The decision tree and all of these trees show the process and how we decide where to make the cuts for the results. But if you are talking about a kind of a univariate example, the result of a decision tree, regression tree, is very similar to a step function. But the step function, I think we just said you draw it at arbitrary lines, right? And so here we'll talk about how these cuts are made, which is less arbitrary, okay? It's made on a greedy basis. Okay, so we'll do this. Okay, so if the explanatory variable is numeric, we split it, x less than k versus greater than or equal to k, all right? And if it's categorical, we'll say x belongs to categories A and B versus x belongs to categories C and D, or whatever categories exist, okay? And so right now, as far as regression trees go, we use it for a numeric response, and the splits that we make, the partitions that we will choose is based on a greedy RSS algorithm, okay? And so for your data, the decision tree will consider every single possible split, okay? So if you have, and it's based on just your training data. So if you have 10 data points in your training data, there is a total of 9 possible splits, okay? Because you could split 1 versus 2 through 10, and or you could split at 1, 2 versus, split between 1 and 2, split between 2 and 3, split between 3 and 4, and so on and so forth, okay? It's going to consider all possible splits, okay? So if you have however many observations you have n minus 1 possible splits, okay? And so I've demonstrated this in your handout with 5 data points, and we're going to consider all 4 possible splits there, okay? And again, and the decision is made using RSS, okay? So here is the data, all right? So our data is 1, 2, 3, 4, 5 for the x variable. So I should say first you kind of sort the values from least to greatest, 1 through 5, and then and here we look at our y, which takes on the values 1, 1, 3, 7, and 8, okay? And so if there's no split, okay, if there's no split, here we get RSS 44. This is basically the same thing as the variance times n minus 1, okay? So yeah, if we take the mean of 1, 1, 3, 7, and 8, the mean of that is 4, and so y minus y hat shows us this, and I'm missing the negative signs over here, okay? But when we square them, you get 9, 9, 1, 9, 16, and so the total of these, the total RSS is 44. Sorry, I forgot the negative signs, okay? So this is what it looks like. Okay, and then, and so what we do is when we do a decision tree, we're going to consider every single possible partition, okay? And so the first one, we will consider partitioning for x less than 1, x less than, I guess, maybe 1.5, okay? So we'll make a partition at 1.5, a split between 1 and 2, okay? And so that means the first observation goes in partition A, and then the other 4 observations go in partition B, okay? And so the mean for partition A is 1, okay? And so it has no RSS, right? It has it predicts this value at 0 perfectly. And then the mean of the other 4 values, if you do 1 plus 3 plus 7 plus 8, and you divide that by 4, you get 4.75, and you take those differences, again, I left off the negative signs, and you square them, and you get this, and when you add them all up, you get 32.75, Okay, so now you get the RSS went from 44 to 32.75. Is that okay? So what has happened here? So it's taken the mean of these 4 values and calculated the RSS. And then we consider the next possible partition, okay? And so the next possible partition splits between 2 and 3 on the x variable, okay? And so these 2 go in one category, and then and these 3 go in the other category, okay? And so the mean of these is 1, and so the prediction value for these 2 is going to be 1, and we have no residual, and so no RSS. And then for the other values, you have 3, 7, and 8, okay? And so the mean of 3, 7, and 8 is 6, and then so you have residuals of basically -3, 1, and 2, and when you square those, you get 9, 1, and 4, okay? And so when you total those up, the RSS of splitting there is 14. Yeah, okay. And then again, we consider every single possible partition. Okay, so here, if we split between 3 and 4, okay, then these observations, 1, 1, and 3 go in the first category, category A, and then the other 2 go in category B, and then their mean values are 5/3, and you square them, and these mean values are 7.5, and so you take the difference and you square that, and you get the RSS of making this split to be 3.1667. Okay, and then you consider the last possible partition, which will be between 4 and 5, and you do the calculations, and then you get the RSS to be 24. Okay. Is that okay? Yeah, question.
Are you, like, I know at the end it kind of, like, we saw like a downward trend of like the RSS.
Yeah.
But like at the end it like went up a little bit.
Yeah.
Are you allowed to make an assumption about like bias and variance?
So, wait, what do you mean by bias and
Right.
variance here?
It looked like before the last example that the more partitions you have.
Well, no. So here, in all of these, we're considering every possible location of making just one split. So the result is always 2 partitions. Either you have partition A and partition B. So here all of these we're only making one split, and it was just with our data set, it just so happened that if I make the split here, okay, the RSS is low, okay? But this is still, the number of partitions is 2, okay? This has 2 partitions, this has 2 partitions. Here we're deciding where we should make those 2, where we should split partition 1 from partition 2, okay? And for this, we are kind of deciding, do I split it between 1 and 2? Do I split it between 2 and 3? Do I split it between 3 and 4? Split it between 4 and 5, okay? And so with 5 data points, there's going to be 4 possible partitions, and we considered all of them in our diagram, okay? And so the one with the smallest resulting RSS after making the split is this one, because if I make the partition here, it's the RSS is 3.1667, okay? But in all of these, I'm still only making one split with 2 partitions, so I'm not, the complexity of the model isn't changing, okay? It's just one split, okay? All right, so this was just kind of a toy example, and we look at, after considering every possible split, requires a bunch of calculations to calculate the RSS every single time, but we consider them all and we say, okay, the one that's going to result in the smallest RSS is the one where we split between 3 and 4, and so that's where we make our split, okay? And so the result of this, indeed, would look very much like a step function, okay? The result of this thing would say, okay, for x less than 3.4, your prediction is, whatever this number is, 5/3, 1.67, okay? And if x is greater than 3.5, then you predict 7.5. Okay, and that's reasonable. Okay, and that's all we're saying. Okay, perhaps if you look at the original data, maybe you could find some kind of function that fits this nicely. Okay, that's certainly possible. Okay, but as far as a rule of thumb goes, you could just say, okay, how do we predict y? Well, just if x is bigger than 3.5, it's going to be 7.5, and if x is less than 3.5, it's going to be 1.67. All right, and maybe that's not perfect. Okay, there's still some residual left, but it gives you pretty good results. Okay, so that's how this works. Okay, it just says so the result looks very much like a step function, but the decision of where to draw the boundary was not arbitrary. It was based on the kind of the reduction in RSS, which split will reduce the RSS the most. Okay, and so that's what we've done. Okay, and R can do this, and you don't have to, like, it was a little bit of a pain making every single one of these tables to figure out all these things. Obviously you don't want to do this yourself. Okay, I mean, you could write a script to do this, and that's basically what these functions do. R comes with, not comes with, but you can install I think I think my notes are, the one I have on screen is it's a little bit okay. So R has this in package rpart and package tree. Now the textbook uses package tree, which works just fine. I think I like rpart a little bit more. It's not covered in our textbook. I have a couple examples. You can use package tree just fine and follow the lab that's given in the textbook just fine. rpart does a few additional things which I think make it a little bit more flexible, adds a few features, but basically you use them in very similar ways. There's just a few things that change when you use kind of the control, and you can read about it. Okay, so here I kind of demonstrate making the tree with tree, and so here it says, so I create our data frame, and then I say make the tree, and you can see up here this thing says 44, okay, and 4.0. This is kind of this says the RSS that you have at the very beginning. This is what we had back here. The mean value for everyone was 4, and then the RSS with no partitions was 44, right? So and that's what this thing here says. Okay, we have an RSS of 44, the deviance, and then the y values of 4. Okay, and then when we make a split, we make the split at 3.5, and then the prediction there is 2.667. I'm not the prediction isn't. The prediction is 1.667, and then the RSS for those nodes is 2.667, which is when we do this, okay, the prediction here is 5/3 or 1.667, and then if I add these up, 4/9, 4/9, and 16/9, that is that's this number, 2.667. Okay, and then for the split at x greater than 3.5, the prediction is 7.5, which is exactly what we see here when we go back to kind of page 5 in the handout, and then the RSS for those two nodes is 0.25 plus 0.25, 0.5. Okay, so So this kind of summarizes basically what we calculated ourselves and things like that. And then when you ask for the summary of the tree, sorry, it got split there. It gives you the residual mean deviance, but basically the total RSS of 3.167, okay, right here. Again, you can do the exact same thing with our part, and it looks pretty much the same. Here, you do y as explained by x, where the data is coming from the data frame, and then you have to tell it our part dot control, and again it does the same kind of split, x less than 3.5 versus x greater than or equal to 3.5 with the same prediction values, 1.667 and 7.5 and things like that, and then and when you ask for the summary though, okay, and I think this is why I prefer our part over tree. The summary gives you a little bit more information, okay? So when you ask, after you do the, make the tree and you ask for the summary, it gives you a couple, a few additional things. One of them is the improvement, okay, 0.928, all right? And that basically says, well, you know what, you started off at 44, and then after you did the split, you were down at 3.167, okay? And so that improvement going from 44 to 3.1667 represents basically 93% or 92.8% reduction in the RSS, okay? Which I think is it's a helpful feature, okay? And then I don't know. It gives you something called CP for complexity parameter, which will tell you like how important are these nodes and these splits. This is almost silly, but you can make plots of your decision trees, okay? So as far as decision trees go, this is about as simple as it goes, and it just has one split, okay? And then the decision question is x less than 3.5? And if it is, you go down this way, and if it's not, you go down the other way, okay? And then the prediction on this side is 1.667, and the prediction on that side is 7.5. You have to call two commands. One is plot, and then the other is text, okay? And text adds the labels. It's not the prettiest thing. There are packages that make prettier trees. What is it? R package. Is it Tree Party? I don't know. It's our package party, okay? And I think they're just being, I think it's party. It's based on partition, and they just made it, I guess, cutesy. Okay. And they make, let's see. I think our package party makes prettier looking trees, okay? With our package party, your trees will look like this, okay? So they make prettier trees. You have to look it up on the internet on how to use it. but they make prettier trees. So there's packages out there that make prettier trees, but I guess if you want a prettier tree, you should probably just draw it yourself. But anyway, this is how you do it. Okay. Okay, so that's the demonstration just on the simplest thing. And so but what do we do for bigger data sets? Okay, well, the regression tree works exactly the same way. All right, so here, let's say you have 5 variables and 100 observations. It's going to consider every single possible partition, okay? And so it's going to consider each variable one at a time and each possible split one at a time. So if you have 5 numeric variables, there's each numeric variable has, assuming no ties, okay, you're going to sort them from least to greatest, and you're going to say, okay, well, let's split it here, let's split it here, 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 here. You got 99 possible splits to consider, okay? And if you have 5 different variables, then you have 495 splits to consider, and every single one will result in a different kind of RSS, okay? And the decision tree is greedy, and so it's going to consider all 495, and it says, this one has the biggest reduction in RSS, or the smallest resulting RSS. I'm going to pick this one, and that's how it makes its first split, okay? And then it splits the data into, one partition over here and another partition over here, and then it goes through and it considers every single possible split over here and every single possible split over here, and the next one it makes is the one that results in the greatest reduction in RSS. Okay, and it just keeps doing this until you reach some kind of stopping criterion. Okay, and the stopping criterion might be something like you need to have at least 3 observations in each terminal node, or you need I don't want you to make more than 7 splits, more a depth of more than 7 or something like that. Okay, so you've got some kind of stopping criterion, but again, the decision tree considers every single possible split. If you've got a categorical variable, then the number of splits it has to consider will be fewer, right? If you have a categorical variable with only 2 things, then there's only one possible split, right? You're going to put like male versus non-male or something like that, okay? Or if it's with something with multi-categories, you can do white versus non-white, or Asian versus non-Asian, or something, something like that. The splits are a lot easier when for categorical variables. I don't want to say easier, but there's probably fewer to consider. Okay, and that's how the decision tree goes, as far as deciding where to draw, how to handle larger data sets. Okay, so decision tree only considers one variable at a time, and it does a split, but it considers every single possible split. Okay, every single possible one, and which is always possible because it's using your training data, so there's always just a finite number of splits. But this means when you have very large training data sets, the decision tree can take a very long time, okay? Because it's considering every single one. Okay, so depending on what you do, you often will get too many splits, okay? So if we do our toy data set, okay, we could technically, depending on the settings that we tell it, we can just say, keep making splits, and the minimum number of, the minimum number of observations you need at each split is 2 or something like that, okay? Well then, in that case, it could result with this kind of function at the end, where it basically split and said, all right, we're going to split at x less than 2.5. Well, first split at 3.5 versus at 3.5, and we got this and this. And then we're going to further split that into those less than 2.5 and those greater than 2.5, and over here, those less than 4.5 and greater than 4.5. Okay? So, oops, I had that wrong. So you can you could do this, and what is the RSS of this? 0, right? There's no error here. We've perfectly fit our data, okay? Now, so we've achieved 0 RSS, but do you think this is a good model that we should keep? Probably not. We've probably overfit the data, and this is a common thing that happens with decision trees. Is depending on what you say, it's very often going to overfit the data. All right, and so so then what you want to do is you want to go back, and you want to do what we call prune the tree. Okay, so they're using all of these gardening analogies, right? And so so pruning a tree in gardening is like, I don't know anything about gardening, but my understanding is that if you want the fruit on this branch to grow bigger, you cut away the other little the little branches, so the tree doesn't waste energy growing like measly fruits on a bunch of branches, but just like a couple big fruits on the important branches or something, right? Something like that. Okay. And so there's something similar here where, you know, we've made all of these splits and we made all of these branches, but we say, you know what, this is no good. Let's remove some of these splits. Let's remove some of these branches, right? Okay. So so the way we do this is we remove what we consider the weakest link, okay? Sorry, I've noticed a bunch of typos here. These should say x equals 4.5, not 7.5. Okay, so wherever you see 7.5, it should say 4.5. So so right now we have at the top we split at 3.5, and then we further split at 2.5, and we further split at 4.5. Okay, and so what we want to do is we want to say, well, which tree gives us which node is the weakest, right? And so from here we can see at the split at 2.5, okay, the total RSS without this split, okay. So for here, if we look above, the total RSS for that node is 2.667, okay? And then after we make the split at 2.5, the total RSS is going to be 0 plus 0. We have 0, okay? So we have reduced our RSS by 2.66, okay, by including this split, okay? On the other hand, if we split at 4.5, okay, the RSS before that split was 0.5, and after we make that split, it's going to be a total of 0, okay? And so as far as which, between these two splits, the 2.5 versus the 4.5, which one has less of an impact, the 4.5 one has less of an impact because we're reducing our RSS by only 0.5, okay? And so, so that one would be the weakest link. That one would be the one that gets removed first, okay? And so again, this is just a feature that appears with when you use rpart, but you get kind of a listing of what they can call complexity parameters, and if you the number of splits, when you include all three splits, the one at 3.5, the one at 2.5, and the one at 4.5, so all three splits, the amount of error that results is 0, okay? But that gives us the smallest complexity parameter of 0.01, which is, in our case, the smaller complexity parameter means a more complex tree, okay? And this kind of shows us kind of the variables there, all right? And so you can use this function called prune, okay? This function prune, it works also for a regular old R tree, and it shows up in the lab, except you don't give it CP, you give it how many nodes you want. You give it best. You give it how many, you know, you tell R preserve the 3 best nodes or the 2 best nodes or something like that, okay? But here we just increase the complexity parameter a little bit, okay? to 0.02, and what happens is we can see it does the first split at 3.5, and it keeps the split at 2.5, but it gets rid of the split at 4.5. Okay, so it gets rid of that one. And then further, if you further increase the complexity parameter, then it says, okay, let's get rid of the split at 2.5, and then and it denotes kind of the tree where there's only one split. Okay, and again, this is just on the super simplified example, but this thing basically works for any more complicated trees as well. Okay. Is this okay as far as what is happening regarding pruning the tree? Okay. So let me open up just the textbook on pruning the tree. Where is it? So this is what pruning the tree does. Okay. This formula. So this part, okay, this part on the left is just a formulas often make things, I don't know if they make things more complicated looking or less complicated looking. You don't have to write this down. Okay, this part on the left, this is basically the RSS. Okay, this is the RSS. It's just you have to, this is each individual value, and this is the value predicted for that partition. Okay, that's what this little symbol represents. Okay, the value predicted for the partition, and you sum it across all possible partitions and all possible nodes in the tree. Okay, so this is basically the RSS. Okay, what is this? This is the penalty for complexity. Okay, and here this is basically just how many terminal nodes. Okay, penalty for complexity, where T is how many terminal nodes. Okay, so normally we would just say minimize the RSS, right? Okay, and that's basically what we do in OLS regression and all of that stuff. But then when we do regularization, we add some kind of penalty for complexity. So this is very much kind of like lasso, okay? Except it's not, the way we calculate the RSS is a little bit different, okay? But it's basically the difference between the actual and the predicted, okay, squared, added up across all possible nodes and terminals and stuff. And here we have the penalty for how many terminal nodes. In Lasso, it was how many coefficients that are non-zero and things like that. And here it's how many nodes that we have. And so here when we do when we prune the tree, we're basically saying that, and then obviously alpha is kind of your tuning parameter, so that if alpha is huge, we're going to say, okay, if you're going to add a node, it better be more than what basically alpha says it should be. Okay, and if alpha is little, then it says, oh yeah, keep adding nodes because the cost of adding another node isn't that much greater, right? So it's kind of just like like the I don't even know, right? Like if you're a company, should we open another store at a new location, right? And the question is, every additional store you open costs money, right? It costs a lot of money, but at the same time, you want to maximize your income, right? And so the question is, well, if I add a store, then I'm able to serve more customers and stuff, and maybe I'll get more money. But at the same time, I'm only going to add the store if the amount of additional money I get outweighs the cost of opening the store, right? And so similarly, we only want to add a node if it outweighs, if the basically the cost of adding the node results in basically a greater reduction in our RSS. Okay, and so this is a formula that just basically says that. I don't know if it makes it easier to see or not, but again, it's kind of similar to the ideas that we have of regularization, where the goal is not just to minimize the RSS, but it's balanced out between how complex is our resulting tree, right? And so that's what we've got. Okay, and then again, the question is, well, how do we pick the complexity parameter when we do our pruning? Okay, and what do you think our answer is? It's the same answer we've been using for everything else. What? Huh? It's arbitrary? Or I guess it depends on the content. Yeah, and cross-validation. that's like our other answer for everything. So how do we decide which complexity parameter, like to what degree of pruning do we do? Well, we can use cross-validation, right? And we can say, well, okay, let's try this amount of pruning and let's try this amount of pruning. So that's what our textbook also says. It says, what complexity, this alpha here, what value of alpha should we use? And it says we can select a value using cross-validation, and this is, I guess, summarized in all of this. And this is why I prefer R part over tree, because R part includes a kind of a cross-validation thing. So here I've used a real data set, okay, and this is I think this is on the cost of a car based on its fuel economy, whether it's a compact car or not, or compact or large car or something. And then here, let me pull up the okay, so this is Consumer Reports 1990. I guess we're looking at 117 cars, and then it's got the price of the car, the country that it came from, and I guess the car can come from Brazil, England, France, Germany, Japan, USA, I guess, Korea, Mexico, Sweden, and USA. The reliability has a few scores: worse, average, better, and much better. The mileage and the type: compact, large, medium, small, sporty, or a van. Okay, And so here we're trying to predict the cost of the car or the price of the car based on these other variables. Okay, and so so our part does a lot of this stuff for us. Okay, and so so first we can just say create the tree. Okay, and it creates a tree like this. All right, and then you can do cross-validation. Okay, and so I think by default our part will do tenfold cross-validation. Okay, and so what does cross-validation look like for us? Basically, here, it's going to split the 117 observations into, a 90-10 split. So probably around 12 observations go into the test set, and so based on the other 105 observations, it creates the tree using some complexity parameter, right? So using different levels of complexity, it's going to make a tree. And so every tree is going to be slightly different, and it's going to make different predictions, and based on the slightly different trees, we get different values of the error that it gets. Okay, and this is what plot CP, the documentation for plot CP, tells us. Okay. Okay, so can I zoom in on this? Okay, well, all right, I don't know how to open this in a browser. Okay, but the rule of thumb here is it says a good choice of the complexity parameter for pruning is often the leftmost value for which the mean lies below the horizontal line. Okay, and so what is this? The CP table contains the mean and standard deviation of the errors for the cross-validation prediction, and these are plotted by this function. Okay, and so the minimum line, which is a horizontal line drawn one standard error above the minimum of the curve. Okay, so when we draw this, so this is the tree that it makes. Okay, by using the kind of the default settings, and then and this is the graph. So as we lower the complexity parameter, okay, which means we get more and more complex models, we have more and more nodes in the final tree, okay, we can see that as we increase the number of nodes, the amount of error goes down, okay, as we expect, right? So as expected, the more nodes we add to the tree, the RSS keeps going down and down and down and down, okay? And actually, but adding nodes 6 and 7 actually doesn't reduce as far as cross-validation goes. The cross-validation error doesn't go down. Okay, so we're not getting much. Okay, and so what we do here, so the lowest cross-validation error happens when we have 5. When the size of the tree is 5 or the complexity parameter is here, okay? But our part, what it also does is it calculates the standard error of this cross-validation error, okay? So it recognizes that the cross-validation error comes with its own standard error and has its own uncertainty. So it goes one standard error above, and it draws a horizontal line here, okay? And so now, the rule of thumb is you pick the so it's possible, this didn't happen here, okay, but it's possible for us to have had a I'm sorry, I picked the wrong one here. Okay, it's possible for there to have been like another node, okay, like right here, okay, something like this, right? And so, so even though this is not the minimum, we would want this one because it's below this line, okay? So we want the leftmost thing where it's still below the line. Okay, that's kind of the rule of thumb. It says a good choice for complexity parameter is the leftmost value for where which the mean, meaning the circle, is below the line. But I messed up and I picked 0.074. I should have picked 0.026. Okay, sorry. That's my bad. Okay, yeah, I don't know what I was talking. I don't know what I'm talking about in this thing. Okay, fix that. Sorry, that's a mistake. So the minimum is at 0.026, and sorry, just delete all of this stuff. Okay. Okay, and so use 0.026 here. Okay, according to. So you look at where this line is, and which circle is below the line. Okay. So, because it's possible that you have the line, and and it goes further down and further up, but you want the one the leftmost complexity parameter that's still below the line. Okay. In our case is 0.026. Sorry, this is bad. Okay. I'll fix that. And re-upload, and upload the fixed notes version. Yeah.
What if there's a point on the line?
Then I don't know. Probably just use the one on the line. That's probably fine. Okay. I mean, it's kind of just like, do I add a node or not, right? And it's kind of like a break-even thing. So. Yeah. I mean, yeah. And cross-validation is just, it's a rough guide, right? And so if somebody else ran the cross-validation, they might get something slightly different, and it might be above or below the line. It's hard to know. So, yeah.
What does the horizontal line?
The horizontal line represents, so often we'll say like, oh, just go with the minimum cross-validation error. That's what we want. But because of cross-validation is the result of a random process, there is a standard error associated with the cross-validation process. And so this horizontal line represents one standard error above the minimum cross-validation. So this is the minimum cross-validation error is achieved here, and this is one standard error above it. And so if there's another value, okay, that is less complex, but still within one standard error of the minimum cross-validation error, then it's probably a good value to pick still. Okay.
So just happen that one is the minimum, and also
Yeah. Yes. And so we would pick that one. Yeah. It's the least complex that is still within one standard error of the minimum. Yeah. So it's the minimum and the least complex one. Yeah. Okay. Should I keep going? Should we take a break? Break? All right, we'll take a short break.